and I am recording. And let me share my browser with you just to show you where we are in the course. Okay, we're currently in week 7. Okay, and again, we talked about counting principles last time, and now we're going to be talking about permutations and combinations in building probability fractions. Again, I want to call your attention to the factorial calculator and the permutations and combinations calculator here. Okay, from time to time, I'll use these to show you how to do it, and I'll also sometimes pull up my TI-84 just because it's easier to show that on the screen with whatever else I'm doing. But the calculators that are embedded in the course should work just fine for doing the probability work that we need to do. Now, I'm going to start by opening probability with permutations and combinations. But before I launch into that material, I want to share with you one aspect of permutations that we didn't get to cover in class, but it is in the reading for the course. And I just want to make sure that everybody sees it. Okay, so I'm going to share that first, and then we can move on to the notes. Okay, so let me, I'm not seeing that. All right, let me share the content with you. Okay, so now everybody should be seeing like a piece of graph paper that says distinguishable permutations. Okay, hopefully everybody can see that. Can you just shout out yes or no? Want to make sure the tech is working. Yes. Everybody, good. Okay, thank you. So what I want to talk about is this concept of distinguishable permutations. If you remember from Tuesday, permutations are sets of objects selected from a set when you're selecting without replacement, okay, and when order matters, okay? So for example, if you're making words out of letters, okay, the order in the word of the letters matters. Same thing with numbers in a telephone number or a PIN, a personal identification number for a bank account. What I wanted to talk about is what happens when some of the letters in the pool are repeated. In other words, you can't distinguish between different repetitions of things in the pool. Here's an example of that. How many distinct permutations can you make from the letters in the word Mississippi? Okay, now you have to think about it. This isn't just 8 permute 8, okay, because what the problem is some of these letters repeat. Okay, so in other words, if I were to use an S in one of my permutations, I can't tell if it's this S, this one, or that one. They all look alike. So there has to be a special formula for distinct permutations. And here it is. Okay, the number of distinct permutations is, is n factorial. And usually the way they put the denominator is you're dividing out the repetitions of different letters. So the first repeated letter, factorial, how many there are, the second repeated letter, and so forth. Okay. That's usually the way they say it. Okay. Where this is the total number of letters in the word. And I'll say in Mississippi, so you know what word I'm talking about. Okay, and these are the number of repeats of each letter. Okay, so let's take a look at how we might use this formula on Mississippi. Okay, and again, I'm showing you this because, well, it occurs from time to time, and I know there's also some problems in the homework that deal with distinguishable permutations. So in our example, N is 11 because there are 11 letters in Mississippi. Okay, and then as far as repeated letters, I have 4 S's. I have 4 I's. Okay, and I have 2 P's. All right, as far as how I'm going to build this probability, it's not a probability fraction, it's a counting. It's a counting of distinguishable permutations. So here's what I do. I put 11 factorial in the numerator, and then here's R1 factorial, R2 factorial, R3 factorial. All right, and then I just need a calculator to evaluate this. Now you can use the factorial calculator that's built into the course. For me right now, it's easier for me to use my TI because I can show that to you quickly. So let me show you that. All right, everybody should see my TI on the left. Okay, and I can type this formula right into the TI. So I'm going to first get a fraction template. And I'm going to put 11 factorial on the top. On the TI, that's in the math menu. And it's the 4th item in probability. So there's 11 factorial. Then 4 factorial. Okay, you don't need the times. So 4 factorial again. And 2 factorial. The only advantage of the TI is I can make it look like exactly what I need it to look like. Okay. You hit enter, and I get that there are 34,650 distinguishable permutations. That means that I can, in other words, if there was one S or the other S first, that wouldn't count as 2 separate permutations because I can't tell them apart. Okay, so this is a smaller number than there would be if there weren't repeated digits or repeated letters. All right, so again, I just wanted to show you this. So if you see the words distinguishable or indistinguishable in any of the problems, okay, please remember this is the formula that you need to use, okay? And this is described in the text, okay, for this section, okay, for section 2.4. So you should be able to see it there. All right, anybody have questions on this? I figured before we go on with probability, let's see if there are any questions on counting. Any questions in general on counting with permutations or combinations? Okay, good. All right, well, here are the notes, okay, about how to use this strategy, okay, to find probabilities. And like I said, when we opened up class, we're going to just combine what we learned about counting with permutations and combinations with what we know about probability. Okay, so the key things to remember, okay, are the basic definition of probability. It's the total number of ways that you can achieve your desired outcome, or the number of ways event E can happen, divided by the total number of possible outcomes, or the number of outcomes in your sample space. Okay, those are 2 ways we've referred to them. Okay, the numerator needs to always be equal or less than the denominator. You're never going to have a probability fraction greater than 1. Okay, both of the permutations and combinations require that we sample without replacement. So they require sampling without replacement. Namely, we're not putting things back in the pool once we select them. We remember from some of the examples we did on Tuesday, if it turns out you are putting things back in the pool, then you need to find a different way to count. Usually you're going to count with the fundamental counting principle. Okay. The difference between permutations and combinations has to do whether order matters in the choice. Okay. You use permutations when order matters, and you use combination when order doesn't matter. Okay. The choosing doesn't matter. The order you're choosing in doesn't matter. Use combinations. If the order is important, like in words or telephone numbers or passwords, you're going to count with permutations. Okay, so that's just kind of a review. And let's take a look at some examples. Okay. A lottery game is set up so each player chooses 6 different numbers from the numbers 1 through 53. Okay, this sounds a lot like Powerball. If the 6 numbers chosen match the 6 numbers drawn, the player wins the jackpot. Okay. So before we even answer the question, okay, let's ask ourselves some things. First of all, are we sampling with or without replacement here? Has anybody ever watched a lottery drawing on television? Okay, usually they have this big bin with the balls in it. Somebody's spinning the bin and then reaches in and takes ball number 1 out. Then they take ball number 2 out. And then they take ball number 3 out, all the way up to the 6th ball. Are they sampling with or without replacement? Yeah, without. Okay. So this is without replacement because the balls don't go back in the bin. You can't choose the number 10 twice. Okay. And then take a look at the way this is written over here. If the 6 numbers chosen match the 6 numbers drawn, okay, the player wins. Do they say anything about them needing to be in order? Okay, what do you think? Do you have to match them in the same order they're drawn, or do you just have to match the 6 balls once they come out of the bin? I guess what I'm asking is if your lottery ticket says 1, 2, 3, 4, 5, 6, and they draw 6, 5, 4, 3, 2, 1, do you win? Yes, you do. Okay. It would be virtually impossible to match them in the same order. Okay. So order does not matter. Okay. Does everybody understand how I made those decisions? Because those are the critical decisions. Okay. It's impossible to get the right answers to these types of problems unless you know how to make these choices. So anybody have questions? Okay, I'm not seeing any. So the probability they want to know with one lottery ticket, the probability of winning, okay, is all the total ways that you can pick 6 out of 53. Okay, and we said we're going to count with combinations because order doesn't matter and we're counting without replacement. Okay, and the numerator is the one way to pick the 6 winners. Okay, you've only got one way to win. Namely, you have to match all 6 of the balls that are drawn. Okay, so my numerator's easy. That's a 1. And the denominator is 53 balls, and I want to choose 6 of them. Okay, everybody see how I came up with that? Okay, the rest of it is something I can do on a probability calculator. I'm just going to evaluate 53, choose 6, and I'm going to go over here to my combination and permutations calculator. It's set for counting combinations. I've got 53 balls I'm picking from, and I want the choice of 6 of those. And I get 22,957,480. Okay, so there's a 1 in 22 million chance that I'll actually win here. Okay, if you express this as a decimal, okay, it's approximately, let me count the zeros. It's 1, 2, 3, 4, 5, 6. Okay, what do you think about that probability? Is this a large or a small probability? What do you think? Yeah, vanishingly small. This is, like I said, 1 in a 22 million chance. Okay, so very small indeed. Okay. All right, so this is kind of the Powerball situation. Now let's take a look at some people's, a lot of people say, hey, you know, Powerball's up to $500 million. I'm going to win. I'm going to buy 5,000 tickets. Well, that's going to cost you like $10,000. And let's see what that does to your chances of winning. Okay, your denominator is still the same. That hasn't changed. The only difference now is you've got 5,000 chances of winning instead of just 1. So I'm going to open up my calculator so you can see what this number is. 22,957,480. It gave it to me in scientific notation, okay? The answer isn't 2.17. See this e to the minus 4? Okay, what the calculator's telling me to do is move the decimal point 4 places to the left. So that's going to give me 0.3 zeros, then the 217. Okay? Everybody see that? What do you think about this probability? Is this probability large or small? Yeah, it's still really small. Okay. So when your odds are 1 in 22 million, buying hundreds or thousands of dollars of lottery tickets doesn't really increase your odds that much. Yeah, it cuts them, it doubles them. At least, you know, you've kind of done it by 1,000-fold here. You've lost 3 of these leading zeros, but your probability of winning that jackpot is still really, really small. Just to remind you, this is the 10th place, the 100th place, the 1,000th place. This is 10,000. So you've got a 2 in 10,000 chance of winning here. Okay, just to give you an idea. Anybody questions about this example? Okay, try to start out with one that, you know, maybe people have experience with, since some people do play Powerball. Okay. Not seeing any questions, feel free to ask them if you've got them. All right. Okay, let's take a look at other examples then. Okay, and I'm going to start out by kind of reviewing the multiplication principle. Or I called it the fundamental counting principle here, right? Okay, and really what that says, if you have more than one choice, okay, and each choice has n outcomes, okay, the total way to make let me call it, the total way to make m choices is to multiply together the outcomes. So here's n1 times n2 times n3 dot 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 n sub m. So you're going to just multiply the number of outcomes from each of the m choices. Okay? And we used that the last time we met on Tuesday when we had groups that were divided into separate subgroups like men and women or teachers and parents, stuff like that. You can consider making two separate choices there to build a larger group. Here's an example. A club consists of 5 men and 7 women, so that's 12 people. 3 members are selected at random to attend a conference. Find the probability that the selected group consists of 1 man and 2 women. Okay, so let's ask ourselves the same questions. Am I sampling with or without replacement? What do you think about this? Are we sampling with or without replacement? Okay, imagine how they might do it. They take 12 people's names, throw them in a hat, and somebody picks out 3 members. Do they put the names back in the hat? Yeah, without. Okay, without replacement, because you can't be picked twice. You're either going to this conference or you're not. Once you're chosen, your name doesn't go back in the hat. And let me ask the other question. Does order matter? Does the order we choose people in matter? Or is everybody doing pretty much the same thing if they're chosen? What do you think? Is order important? Yeah, no, order is not important because if you're chosen, you're going to the conference. There's nothing special about being chosen first or second or third. So no. Okay, so if it's without replacement and order doesn't matter, I count with combinations. Okay, make that decision first. Then we can build the probability fraction. And I want the probability of 1 man and 2 women. So that's going to be the number of ways I can make that happen over the total number of ways to choose 3 out of 12. Okay, so the denominator is all the different ways to choose those 3 people, regardless of whether they're men or women. So that's 12, choose 3. Okay, then up here, I have the number of ways to choose men. And on top, the number of ways to choose women. Okay, and that's where I'm going to use the fundamental counting principle. You can see I'm making 2 choices there. So I'm multiplying the number of outcomes together. All right, so this is 12, choose 3. I'm interested in choosing one man out of the 5 that are available, right? You can see down here, find the probability that the selected group consists of 1 man, and there are 5 men, and 2 women, and there are 7 women. Okay, so that's kind of telling me the R and the N for my combinations in the numerator. Okay, so I have 5 men. I'm interested in choosing one of those. And I have 7 women, and I'm interested in choosing one of those. Okay, before we actually calculate this probability, let me ask you a question. Based on, I mean, you can actually see the structure of the group, and you can see there are more women than men. What do you think this probability would be? Do you think the probability should be very low? What do you think? Okay. You think the probability should be low? No, why not, Logan? You're right. Okay, there are more women in the group, and there are going to be more women in your sample. Okay, so when your sample, which is our 3 people that we're picking, looks something like your group, that tends to make the probabilities a little higher. So I would say our probability should be pretty close to a half here. Okay, but let's see what we get. Okay, again, if you're using the built-in probability calculator, the built-in combinations calculator, you're going to need to find these individually. Okay. I'm going to show you on my TI because I can bring it up while we actually have the notes open. And I think that's a little clearer than going back and forth to the separate screen. But again, you do have a combinations calculator. It's just you're going to need to write down the large numbers, okay, here and here, and keep track of them. Okay, so if I want to do this, I'm going to, first of all, open up a fraction template because I have a probability fraction. And then I'm going to use combinations. So I first put in my N value, use the math menu, go all the way over to probability, pick NCR, and then put in the R value. I do need a multiply here on the TI-84 between combinations. And then it's going to be 7 NCR 2. That's on the top. So that looks like what I've written here. And then I'm going to go into my denominator and get the number of ways to pick 3 out of 12 people. Okay, so that fraction looks like this fraction. Then I'm going to hit enter. Okay, because I use the fraction template on the TI-84, it renders the answer as a fraction. Okay, which of course you just need to divide 21 by 44 to see what it is as a decimal. Whoops. Meant to divide that. Okay, and you can see it's almost 0.48, which is really close to half. Okay, so we did get a probability fraction that's really close to half. Anybody questions on this? Questions on this one? Okay. All righty. How about you try one? Okay. I'll leave this one up here. And I'll write it here. You try. Let's see. I don't know if they call them PTAs or PTOs here, but let's call it the PTO, Parent Teacher Organization. A PTO has 42 parents and 6 teachers. What's the probability of randomly choosing a committee with 4 parents and 1 teacher? All right, so you try this problem. Okay, everybody see the one we're trying? We're trying this one right here. Okay, and it's done almost exactly like the one above it. Okay, so you can use the club example to help you. Okay, please do me a favor, type done when you finish this. Okay. We'll take another half a minute. Okay, everyone, let's come together. I realize some of you are still working, and that's fine. But let's come together to be sure that you know how to set this one up. Okay, I'm going to build the probability fraction right next to it. Let's take care of the denominator first. Okay, basically, I want to choose, okay, a committee of 5 people out of a total of 48 people. Okay, the 42 parents and the 6 teachers. So my denominator is going to be 48, choose 5. And again, just like the example with the men and the women in the club, this is an example where I'm not replacing people back in the pool if they wind up on the committee, so it's without replacement. And again, it's a committee, no special roles for anyone, so order doesn't matter. Okay, I thought everybody would be able to see the parallel to the club example. All right, so there's a total of 48 people, and I need to choose 5 of them for the committee. They're broken into parents and teachers, so I want to choose 4 out of the 42 parents, and I want to choose 1 out of 6 teachers. Okay, you'll notice with these probability fractions, the one I just drew here and the one up here, the n values in the numerator in general will add up to the n in the denominator. See, 42 plus 6 adds up to 48, and the r values will also add up. So 4 plus 1 is 5. Likewise up here, 5 plus 7 is 12. And 1 plus 2 is 3. That's a sanity check that you set it up right. The only examples I can think of that aren't like that are where you're talking about poker hands, because you're making more than one choice. You're choosing a suit and then you're choosing a card. So it's not as simple as these fractions, but most of the examples you're going to see have that property. Okay? Anybody questions on how I got the probability fraction? Once you get here, it's just a calculator problem. You just need to find the combination values and keep track of them. So again, if I do it on my TI-84, my numerator is going to be 42, choose 4, times 6, choose 1. On the top, and on the bottom, it's going to be 48, choose 5. Okay, so that fraction looks like what I wrote down on the paper. And then I just hit enter. And I get about 0.3922. About. Okay. In general, if you're gonna enter your probabilities as decimals, carry about 4 decimal places. Okay. Anybody have any questions about this one? Questions on the one you tried? Okay, no questions. Okay, well, let's then look at different variations on how you can do these fractions, probability fractions. A lot of the variation has to do whether order matters, whether you're sampling with or without replacement. And then we'll introduce the concept of rather than picking an exact number for your numerator, right? Like suppose I wanted a committee with at least 4 parents. Okay, that means I'd be okay with 4 or 5 parents on the committee. That's a slightly different computation. Okay, so we'll talk about using those terms. All right, example 1 is a psychologist claims she can teach 4-year-old children to spell 3-letter words quickly. To test her, one of the children in her class was given cards with the letters A, C, D, G, and O on them. Okay, so these are the only letters the child has. What is the probability that the child will spell dog purely by chance? Okay, this is kind of like the example you might have heard of. If you lock 100 monkeys in a room with 100 typewriters, they'll eventually start typing Shakespeare. Yeah, no. Okay, it would probably take millions of years for that to happen by chance. Okay, and you'd need a lot of bananas. Okay, so anyway, let's take a look at this example and ask some questions with or without replacement. And how would you decide? What do you think? Okay. What do you think in this example? Imagine how this test would work. You give the child the 5 cards and ask the child to spell a 3-letter word, spell dog, and the child puts down 3 of the cards. Does the child put any of the cards back so he can pick them again? No. Okay, yeah, so this is without replacement. Okay, you'll notice also there are no repeated letters in the 5 cards. Okay, so without replacement. Does order matter? When you're spelling a word, is the order of the letters important? Yes, okay. If the child spells G-O-D instead of D-O-G, we're not going to give him credit for spelling dog because that's a different word. Okay, so in words, order does matter. Okay, so we're choosing without replacement and order does matter. That means we need to count with permutations. Okay, everybody see how I picked that? Okay, so we want to know the probability that the child spells dog. Well, with those letters, there's only one way to do that. Okay, and that's the child puts down D-O-G. Okay, no other selection will work. And in the bottom, we have the total number of ways to choose, I guess I should say permute 3 of 5 letters. Okay, so that's 1 over 5p3. And again, if I go to my permutation calculator, here I'm going to count permutations. Okay, and I have 5 things and I want to permute 3 of them. I get 60. Okay, 60 permutations. Again, not sure why things are jumping around. Okay, so this is 1/60th. What do you think? Is this a high or a low probability? High or low probability? What do you think? Is this likely to happen or not? Anybody have any thoughts? Well, you can always take 1/60th and render it as a decimal, and you get 0.016666. Okay, which is a little bit more than 1.5% chance. Okay, so that's a pretty low probability. Okay, low probability the child will do it just by chance. Okay, so if this kind of gives you an idea of how you would test the validity of the psychologists claim. In other words, if you have your child do these tests, maybe over the course of a couple of weeks, the child does it maybe 20 or 30 times. If there's more than a 1% success rate, 1 or 2% success rate, then the child's probably actually spelling. Okay, if the child gets 35% of them right, the child's learning how to recognize letters. If the child is just getting about 1%, 2% of the words right, then they're probably just guessing. Okay, that's more of a statistical thing, and we'll talk about things like that a little bit later. Okay, and you definitely will see stuff like that in a more advanced statistics class. Here's another example. Okay, suppose that all license plates in a state start with 3 letters followed by 3 digits. Okay, so these are like the old Arizona plates before we added the 4th digit. Okay, if a license plate is chosen at random, what is the probability that all 3 letters and all 3 numbers will be different? Okay, so let's start asking some questions. Okay, when we actually make a license plate, are we creating the license plate with or without replacement? So what I'm asking you is, on a license plate, can the letters and the numbers repeat? Okay. Yes. Okay, so this is with replacement. Okay, when we're talking about the total number of plates, all right, so I don't even need to add that about, order, whatever. So the total plates need to be counted with the fundamental counting principle. I can't use permutations or combinations for that. Okay, but now let's look at the number that we're interested in. Okay, let's take a look. All 3 letters and all 3 numbers will be different. Okay, so basically, as far as this is concerned, is this with or without replacement? Okay, if I'm interested in 3 letters and 3 numbers being different, am I putting the letters and numbers back in the pool? Yeah. I'm not. Okay, so this part is without replacement. And on a license plate, does order matter? Does order matter on a license plate? Really, if I have, are these 2 separate license plates? Suppose I have a license plate that's CAT123 here. Let me type in the chat. Okay, are these 2 plates the same? CAT123 and TAC321. Are they the same license plate? They contain the same letters and digits. Okay. Yeah, no, they're not the same plate. Okay, that tells you that order does matter on a license plate. Okay, order does matter on a license plate. Okay, so for the part where I'm interested in, okay, plates with all three letters and all three numbers different, I'm going to count with permutations. Okay, so again, this is a slightly different scenario where you're not using the same counting method for the numerator and denominator. 3 unique letters and 3 unique numbers. Okay, so let's see how we would build that. Let's consider a plate where we're allowing all letters and all numbers to repeat. Okay, that's the denominator. That's the total number of ways to select 3 letters out of 26 and 3 digits out of 10, allowing for repetition. Okay, so let's say here are the places on the license plate. There's 6 places, and let's say it's 3 letters first. I have 26 choices for the first one. And if I allow repeats, 26 choices for the other 2. Okay. When it comes to the numbers, I have 10 choices for each one of those places because I'm allowing the digits to repeat. Okay, that's for the total possible license plates. Now, the ones you're interested in are the ones where the letters don't repeat and the digits don't repeat. So you're going to use the fundamental counting principle up here, and you're going to consider letters separately from digits. Okay, and we said this part we're going to count with permutations. Okay, so I have a total of 26 letters, and I'm interested in 3 of those being permuted. Okay, so the idea is you pick a letter, you throw it out of the pool. You can't pick it again. You pick another letter, you throw it out of the pool. Okay. Some people would say, isn't that just 26 times 25 times 24? And it's like, yes, that's what you'd get from the permutations formula. Okay. Same thing with the digits. You've got 10 of those and you want to permute 3 of them. So you pick a digit, it goes on the plate, and then you throw that digit out of the pool. You pick a second digit and so forth. That's going to be the same as 10 times 9 times 8. Okay. Everybody see how we set it up? Everybody see how it's set up? Okay, and then the only thing I'm going to do is use my calculator to actually do the arithmetic. Okay, so my top is going to have permutations, and you can use your permutation calculator for that. Okay, so 26 permute 3 times 10 permute 3. Okay, so that's the unique letters and unique numbers, no repetitions. And down here, I have 26 times itself 3 times. That's 26 cubed times 10 cubed. Right? Everybody's okay with the exponents here. The exponents just handle the repeated multiply. Okay, and that gives me a result of 108 over 169, which is approximately, as a decimal, 0.6391. Okay, that's a pretty high probability, don't you think? Okay, we're saying I have better than half probability of randomly choosing a license plate that has no repeated digits and no repeated numbers. My question to you is, why is the probability so high? Why is the probability so high? I mean, feel free to unmute. You don't have to type a long answer in the chat. Why do you think? Anybody have any thoughts? Part of the reason I ask you these questions is so you can develop an intuitive sense about the numbers that are coming out of your calculations. If you just look at it and you say, I don't know, I guess it must be right, you really have no way to detect when you've made a wrong assumption. Okay. But if you develop an intuition about, well, yeah, that's reasonable because, then you can look at a number and decide, yeah, that's right, or no, that's garbage. I should really check that. Okay. And that's really important when you're using statistics. You're probably going to get your statistics out of a computer program, right? You're going to need a really a strong sense of whether or not your numbers are valid or not. Okay, I don't know how else to tell you that. Don't just blindly trust what comes out of a computer or a calculator. Okay, because garbage might have gone in. In this case, the reason the probability is so high is because there are so many letters and numbers to choose from. Yeah, it's because the letters and numbers are supposed to be different. The probability of repeating them is low. Okay, so it's, yes, you're right. It's the it's because there are so many that the probability of repetitions is low. Okay, because there are so many of them to pick from. So it's likely if you're choosing letters, you're only choosing 3 out of 26. So it's likely you'll pick 3 different ones. Okay, it's slightly less likely that you'll pick 3 different numbers, but still you're only choosing 3 out of 10. Okay. Another way to break this down is to actually split it into 2 separate fractions and see what's the probability of getting unique letters. That's going to be much higher than the probability of getting unique numbers. Okay, but when you put them together, you still get a fairly high probability. Okay, does that make sense? What do you think? Makes sense? Yeah? Okay. All righty. I have another one I would like you to try. Okay, so this is one that I'd like you to try. Okay, 2 openings exist on an appellate court, that's a court where you appeal a case to, are to be filled from the current municipal court judges. The municipal court judges consist of 23 men and 4 women. Okay, so we want to pick 2 out of these total of 27 people. We want to find the probability that both are men, and then the probability that one is a man and one is a woman. Okay, so here we want probability of 2 men. Okay, and here we want the probability of 1 man and 1 woman. Okay, and again, you want to ask yourself the questions. Okay, with or without replacement. What do you think? Are we selecting with or without replacement here? In other words, once we pick a judge's name, okay, from the municipal court judges, are we going to put his or her name back in the hat and pick them for the second slot on the appellate court? What do you think? Without. Okay, does order matter? Okay, what do you think? Okay, there are two appellate court openings. Okay, it doesn't matter who's selected first and who's selected second. They're both going to be appellate court judges. Okay, so the fact that we're sampling without replacement and order doesn't matter. Count with combinations. Okay, so again, you try this one. All right, type done when you finish. Okay, there's two parts, A and B. All right, type done when you finish. We'll take another minute on this problem. Okay, if I could just get some feedback from you, I need to know if you're still working or if you're stuck. Are you still working or are you stuck? Could you just let me know that? Good, thank you. We'll take another 30 seconds or so. Okay, folks, I know you're all still working, and that's fine. But let's come together because there's one or two more things I want to show you after this. So let's just come together and make sure we're all on the same page with this problem. Okay, again, what I'm trying to do in part A is find the probability of picking a sample of 2 that's just men. Based on the selection of judges in municipal court, okay, do you think it's likely that I'll randomly pick a sample of 2 that's all men? How likely is part A to happen? You think that's going to be a high probability? Anybody have any opinions? Yeah, it is going to be likely because the municipal court judges are mainly men. Okay, so it's going to be very likely to pick 2 at random who are both men. Here's the probability fraction set up. So it's the way to choose 2 of 23 men and no women. Okay, I put this combination in here, 4 women choose 0. There's only one way for this to happen, and that's to choose no women, okay? So I know this combination is only multiplying by 1. I put it in there for completeness. This is the way to choose 2 out of 23 men. And the denominator is the way to choose 2 out of the total 27 people, regardless of whether they're men or women. Okay, and then on the calculator, I would just evaluate this. So I have 23, choose 2. Times 4, choose 0. You'll notice when I build my probability fractions, I don't like evaluate the numerator and then divide the numerator by the denominator. I try to put it in all at once. Okay, so what I suggest you do if you're using the online tools I gave you is get the combinations from the combination calculator. You've got 3 combinations in this fraction, write them down. Okay, and then go to the Web 2.0 calculator and put everything in at once. Okay, so you would have the numerator in parentheses with these 2 combinations multiplied, and then divide that by the denominator. Okay, don't do separate operations. Okay, the more operations you do separately, the more chance there is for getting rounding errors. Okay, so try to put your numbers into the calculator all at once. Okay, so for this one, I got 253 over 351, which is a number that's about 2/3 if you look at the first digits. Okay, so this is about 0.72. Okay, so that's a very high probability. And it makes sense because our group that we're pulling from is almost all men. Okay, so it's reasonable we get a high probability. Okay, for the second half of the question, they wanted the probability that we would get 1 man and 1 woman randomly. And I would expect this to be a lower probability than part A, because again, there just aren't that many women in the group. Okay, so here's the probability fraction. It's 23 men choose 1 of them, and 4 women choose 1 of them. So the only thing that's changed in the probability fraction are the R values. Okay, everything else in the fraction is exactly the same. Okay, including the denominator. Okay, if you're using a TI-84, that makes things real easy because I just go back to my original probability fraction, and all I have to do is go in and change my R values. I don't need to retype everything in again. Okay, and this gives me 92 over 351, which you can see is smaller than what we had before. This is about 0.26. Okay, so a good bit less likely. Okay. Anybody got questions on A and B? Anybody got questions on either of those parts? Okay, the one I really want to show you is part C. Okay, and that's this one with at least 1 woman. Okay, so at least 1. Okay, so at least 1 woman is appointed to the 2 appellate or positions. Okay, at least 1 woman is appointed. Okay, what does that mean? Okay, what does at least 1 mean? What does at least 1 mean? Anybody have any thoughts? Well, what would be a number of appointed women that would work? What would be a number of appointed women that would work? To have at least one. Anybody have thoughts? Still got 13 people on. How do you use this in English? Okay, what we're saying, we want to appoint at least one woman to the 2 open appellate court positions. At least one woman. Okay. All right, anybody else have thoughts? Okay, there are 2 openings available, and we're saying we want to appoint at least one woman. Okay, at least one woman means
Two, it could be both
it could be
positions.
both. Yeah, at least one woman means one or more. Okay, and since we've only got 2 open slots, in this case, it means 1 or 2 women. Okay, at least means 1 or more, but in this case, since there's only 2 open slots, okay, we can have either 1 or 2. So the probability of at least one woman is done like this. Okay, it's the probability of exactly one woman and, or, right, or rather, probability of exactly 2 women. So again, the probability is slightly higher than either of these separately, okay, because you've got a choice. Okay, we can either have 1 woman on the appellate court or 2. Okay, now you might notice from part B, okay, that was the probability of 1 man and 1 woman. So we have this probability. Right, because the other person has to be a man then. Okay, and from part B, we got that to be 92 over 351. We know that part. So all we need is this probability, the probability of exactly 2 women. All right, so I'm going to find that probability. Okay, that's going to be of the 23 men on the court, we're not choosing any of them. Okay, and of the 4 women on the municipal court, we're choosing 2. We have the same denominator, 27, total people, choose 2. So again, the only thing I'm changing are these R values. Okay, so let me do that on my calculator. All right, I'm going to go back to my probability fraction because I don't want to type it over again. And I'm just going to go backwards and I'm going to change the R values again. This is going to become a 2 because I'm selecting all of my judges from the women. And this will be a 0 because I'm not choosing any of the men. And you see I have 2 out of 117. Okay. And these would be added together. Okay, and again, I can do that on my calculator as well. Okay, and again, I'm just taking the decimal answer. Okay, out to 4 decimal places. So this is the probability of selecting at least one woman. You'll notice it's slightly higher than selecting exactly one woman, because now I have this very small probability that I choose both of them as women. Okay, so when you see at least, you think, well, there are alternatives, so I might want to be adding probabilities. There's one other way to do this that's quicker. Okay, and that's this way. At least one is one minus none. Okay, remember we talked about the complement principle, that if you are interested in something not happening, you're going to subtract it from one. Okay, well, in this example, at least one means one or two. What's left over? Well, there's the possibility that no women wind up being chosen. That's the only thing that would be left over. Okay, so at least one is one minus none. Okay, so I'm going to say the probability of at least one woman equals one minus the probability of no women. Okay, everybody understand the logic of that? Okay, at least one is one minus none. Okay, the probability of no women, I already have up here, namely the probability that both are men. Okay, and this was actually 0.7208. Okay, so I'm going to subtract that from 1. This is from part A. Okay, and if you do that on your calculator, you should get the same value we got by adding things up. Which is 2792. Okay, so there's more than one way to do these at least problems. Okay, you can add up the alternatives, but I was lucky here that there were only 2 appellate court positions open. Okay, suppose there were 10. Okay, then I'd have to add up 10 separate probability fractions. That takes long. It's a lot faster to just say at least one is one minus none. Okay, and then I just have to calculate the probability of no women, and I have my probability value. Okay, so let me ask you questions on part C. Okay, please ask if it's not making sense. We'll definitely use this. Okay. Not seeing any. I'm going to go through the rest of the problems kind of quickly because we're getting near the end. I just want to show you how to set them up and what hidden assumptions might be in them, because to be honest, that's more important than actually going through the calculating. Okay. I will upload all my work on these notes, so you'll be able to see everything worked out in detail. Okay, so let's look at this. Suppose I have 6 transistors, which are little electronic components, that I'm drawing at random from a box that contains 18 good ones and 2 defective ones. Now, this is kind of like a quality control example. okay, where you're going to do some testing on your transistors. So what you're going to do is you're going to randomly pick 6 out of the box. You're not going to put them back because they're being tested. So this is with no replacement or without replacement. Okay, and the order doesn't matter because every transistor is going to be tested. All right, so we're going to count with combinations. Okay. Now you might be sitting here saying, how do they know there are 2 defective ones in the box? Well, hopefully they didn't just put 2 defective ones in the box, but they know based on their shipping statistics over a long duration of time, they know what their failure rate is. Okay. That's a pretty high failure rate. Okay. That's possible. The box has no bad transistors, but let's assume for the point of this example, we know this box has 20 transistors in it and 18 are good and 2 are defective. Okay. So to find the probability that all 6 are good, we want to first find the number of ways to choose 6 out of 20. That's the denominator. And then we're going to divide them into good and bad. Okay, 18 of them are good. And we want all 6 of those to be chosen, right, from the good ones. All right, there are 2 defective ones, and we don't want to pick any of those. So that's how we would build that probability fraction. Once we get to this point, it's strictly a calculator question. Okay, so the interesting part is done by the time we get here. Okay, so I'm not going to work it out. Okay, let's look at this example. Can we pick a sample of 6 so that none of the transistors are good? Okay, so basically we're saying we have the same good, bad here. All right, and I'll say we have 18 good ones and we have 2 bad ones. Okay, is it possible to say I want none of the good ones and 6 of the bad ones? What do you think? Is this possible? Is this possible? In particular, is this possible? No. Okay. Remember we said your n value has to be greater than equal to r. Okay. If you put this in a calculator, you'll get a 0. Okay. Which is kind of adequate. All right. You want this to be a 0 probability. Okay. This probability is 0. Can't happen. You don't have enough bad transistors in the box. Okay. Exactly 4 of the transistors are good. Well, that means 2 are bad because you have a sample of 6. Okay, I have the same 20, choose 6 on the bottom. Divide my numerator into good and bad. Okay, 18, choose 4. And it is possible to get both bad transistors. That's okay. It's all right for n to be equal to r, but it just can't be less than it. Okay? So that one's possible. And exactly 2 of the transistors are good, are saying, and 4 are bad. Okay, that's not going to be possible either. Let's take a look why. Okay, I have 18, choose 2, that's okay. And I've only got 2 bad transistors. Here are the good ones. Here are the bad ones. Okay, I can't do this, right? Because again, n needs to be greater than or equal to r. All right, so this would also be 0. Okay, so the probability of exactly too good is 0. Okay, and again, your calculator will help you here, because if you type this into a combinations calculator, you should get 0 or an error. Let's try it. I'm counting combinations. And I say I have 2, and I want to choose 4 out of that. And it says error. The number of sample points cannot exceed the number in the set. Okay, so this calculator gives you an error. The TI-84 gives you a 0. Okay, which if you go blindly along will actually make your probability fraction work out. Okay, but if you get this error message, that means it can't happen. Okay, and the probability of it is 0. Okay, everybody understand that? Okay. Right. Okay. All righty. Let's just wrap it up with a little bit of stuff on poker. Okay. Now, just to get a handle on this, okay, dealt means without replacement. Okay, a poker hand has 5 out of 52 cards. Okay. And also order doesn't matter, because usually what you do when you're dealt a hand of cards is you put them in the order you want them in. Okay, so we're doing without replacement, order doesn't matter. We're going to count with combinations. Okay, now these probability fractions are a little bit different. Okay, because in some cases we need to calculate a suit first. But let's start with part B. Okay, my denominator of my probability fraction is all of the 5-card poker hands. So 52, choose 5. Okay, and that's a huge number. Okay, it's over 2 million. Okay, the number of ways to get 4 aces is to pick all 4 aces and one of the remaining 48 cards. Right? So there's 4 aces in the deck, but you need to get a 5th card. So you're going to pick one of those. So this would be 4. Choose 4. That's the 4 aces. Then there's 48 cards left in the deck, and I don't care which one I get. Okay, so here's one of the remaining 48 cards. All right, so here are your aces, and here's the remaining cards. Okay, the other 2 examples, part A and part C, involve suits. Okay, so when you have to do this with a suit, okay, you need to pick the suit first, then the cards. Okay, so let's take a look at how I would do this. I want to get 5 hearts. I don't care which 5 hearts, okay? But I want hearts. My denominator is the same number, 52, choose 5, the number of poker hands. And I'm going to pick the suit first, okay? There are 4 of them. So this hearts is one suit of 4 possible. So here's the suit, 4, choose 1. And yes, it would be the same if you wanted 5 diamonds or 5 clubs or 5 spades. Okay, so you're picking your suit. And then you're interested in picking the cards right? 5 of 13 in that suit. 13 in the suit, you pick 5. Okay, so you're picking the suit first, and then you're choosing the cards in that suit that you want. And again, since you don't care which cards, okay, you can pick any 5 of the 13. Okay. Anybody have questions about this example? Just in case you see poker problems like this. Questions on these? Okay. Not seeing any questions. Okay. Okay. What I'm going to do then is I'm going to come back to the meeting because we're at time. I'm going to come back to the meeting and ask if you've got any questions at all. Any questions at all?